Hello everybody, Chloethedev here, Chloethedev Unfiltered. We're going to be continuing with a paper review of the ghost paper. And so we are going to chapter 7 now, Probabilistic Liveliness. I decided I'm actually going to go through the appendix after this, and so you know what, I'm just going to get started and not take so long like I normally do. In this section, we prove probabilistic liveliness of our main protocol GASPER from section 4, given some assumptions. Our proof consists of the following steps. So we have 3 steps here. Step 1, assumptions lead to high weight after first slot. Under good conditions, such as having enough honest validators, synchrony conditions, and etc., to be formalized, honest validators have a high probability of finding a block with a high weight after the first slot. Okay. High weight after first slot leads to higher probability of justification. If we have a block with high weight after one slot, its weight differential over competitors is likely to increase throughout the epoch, meaning that this block or descendant is likely to be justified. Just meaning that if you have a block that's going to have the highest weight, and everyone's going to continue voting for the block with the heaviest weight, then that block is going to probably continue getting heavier and heavier and therefore be justified. And then 3, high probability of justification leads to high probability of finalization. So again, if every epoch is likely to justify a block, then eventually it is very likely for at least one block to be finalized in a stretch of n epochs as n increases. So, you might not, with probability, even if you don't have finality for a really, really, really long time, what they're saying is, in this 3rd step, you should still, according to probability, get finality eventually if blocks keep getting justified. This division is not just organizational, it also encapsulates the assumptions into different parts of the argument so that each part would remain true even if assumptions change. For example, the main theorem corresponding to the 3rd item, Theorem 7.5, does not make any synchrony assumptions and also only relies on the probability P that a block gets justified. Those synchrony assumptions may be required to bound P given the previous parts. Also, we assume in the 2nd part, as we do for simulations in Appendix B, that all validators have equal stake, whereas the 3rd part does not. Fair enough. This section is the most intricate and dependent on parameters. For one, the current planned implementation for Theorem 2.0 actually avoids much of the analysis in this section due to the attestation consideration delay. See section 8.3. Also, the bounds assume equal stake per validator, which may or may not be realistic depending on external factors. So I think that's unrealistic because, at the beginning it'll be true, but once you have some slashing, it probably won't be true anymore. However, it is still worthwhile to include an analysis for the pure protocol because the strategy here using concentration inequalities is very generalizable to a whole class of these potential slot-based approaches to proof of stake. And we believe it captures the heart of what makes these approaches work probabilistically. In fact, fixes such as the aforementioned attestation delay exist primarily because of the types of attacks against the pure protocol that we mentioned. So it is useful for intuition building to address these attacks even if the actual implementations avoid them. So we're going to be going through theory regardless of whether implementation needed or not. Thus, the primary value of this section is as a proof of concept of the analysis involved in designing probabilistically live protocols such as GASPER, as opposed to a mathematical guarantee of the actual implementation. So, as we get into 7.1, I'm actually dropping a lot of frames. That's crazy. My internet must be actually going quite slow. Maybe I need to close my laptop. That usually helps. No point having all these devices using data if I don't need to. Anyways, you have probabilistic liveliness preparation, the equivocation game. We define the equivocation game to be the following. Oh, man. Always happens. Once I start doing this, I start yawning. The game is parameterized by, I guess, V, the validators, A, and then a couple numbers. Anyways, you V the validators, and these are some real numbers that parameterize the network. Synchrony conditions. So these are the synchrony conditions. For ease of reading, we push the details to appendix. Okay, fine. We don't care what these numbers are. As in GASPER, the element of the validator is n, and each validator is in the set of which is a set of validators, has some fixed stake, the weight of the validator. Okay, so the set of all validators is n. The total stake of the set of all validators. We assume the total stake is n, so the average stake is 1. So we're assuming that all validators have the same average stake of 1, and the total amount of stake of honest validators is at least 2 over 3. So it doesn't really matter what the stake is. We're assuming all validators have an average equal stake, and over 2/3, or at least 2/3 of them are honest. There are 2 options to vote for, which we call O1, O2 for short, option 1 and option 2. These are abstractions for voting on 2 conflicting blocks in GASPER. So say in GASPER we have 2 conflicting blocks. You can only vote on block 1 or block 2. Very simple. And the concept of blocks are not included in this equivocation game. So it's option 1 and option 2. We, meaning the honest validators, will win if either O1 or O2 obtain at least 2/3 stake worth of votes. We lose if we are in a state of equivocation. So basically, the attacker of the network pretty much just wants the network to stay in a state of indecision. So say, you and your friend are going to McDonald's trying to choose what you want to eat. The menu's so large, you don't know what to pick. But you finally made it between 2 options. You've got to choose one. You win if you get to go pick one and eat. You lose if you sit there for hours starving to death, not knowing. And so the attacker can win in many ways by keeping these nodes indecisive. Note that this is the equivalent to the idea that there is a stake differential of n over 3 between the 2 choices after the game. The equivocation game is defined to capture the idea of GASPER with just 2 choices in 1 slot. Okay, so most of the necessary assumptions for liveliness are encoded into the game so that other liveliness results in this section can be as independent as possible. In the appendix, we are going to flush out the details of the equivocation game and conduct the simulations of equivocation game with 3 regimes: a pessimistic regime, an optimistic regime, and a regime in between. 3 general scenarios. The main idea is that under reasonable conditions, the validator with these, these real numbers, it is very likely that after the first slot, we win the game, meaning that we should expect one of the pairs in GASPER to have at least 2 over 30 worth 2/3 worth of stake supporting it after the first slot. So basically saying after 1 slot, you should have enough nodes, at least 2/3 of the network, acting honestly, and they have voted on that slot, saying this is their belief, this is the correct state of things. Remark. Clearly, the concept of equivocation games can be generalized, and similar games can be used to study other proof-of-stake models. There are many directions, and the protocols for honest validators, latency modeled by something more than the uniform distribution, etc., which may be interesting to study for future work, but may be too distracting for the purpose of this specific paper. Fair enough. 7.2. High weight after first slot leads to justification. So first we think we're going to have high weight. Now, what does that high weight give us? That high weight gives us justification. So in this section, we focus on the, certain epoch, whatever, where T is this certain justified epoch. let S equal the total weight of that, committee, define epoch. We define the following set of assumptions, which we call the assumptions epsilon. The network is half synchronous starting at a certain time. So this is the first time here. And that time equals the justification, like the time where you justify. Anyways, so you are half synchronous at that justification time. Each validator has one stake, and the total number of Byzantine validators is equal to less than a third, meaning that the average number of Byzantine validators in each slot's committees, right? Remember, because each slot has its own committee, is S, which is, the total number of network weight over the committee, over 3, minus that little number, which all that really means, in my opinion, is it's just less. So less than 1/3 of the nodes can be malicious, okay? So for each slot, all the slots going up till you need to for all the committees, or for each I at least, we're assuming that slots, so the element of those, define H for I, okay, fine, so I is going to be 1, going all the way up to C minus 1, so you're not going to have as much as C. Define that to be the number of guaranteed honest attesters in slot, that's the slot, plus 1, so the next slot, and BI to be the number of dishonest attesters in that same slot here. Let S equals N over C, which we already saw above. So for all I, okay, so for each slot, the total number of honest validators, attesters in the slot, plus the total number of dishonest attesters in the slot should equal the total weight of the slot, I would assume. We show that the distribution of honest over dishonest attesters should not stray too much from expectation in proposition 7.2 using ubiquitous concentration inequalities. So time for some math. And this is where, I'm not going to sit down and do the math. I'm not going to lie to you. I just read through it. If I do feel the need to go sit down and do this math, I guess I would. If I was doing some implementation of my own, I'm not there yet in my research. I am simply trying to get through all this data, this research, understand it from a high level, maybe even a medium level when it comes to this Ethereum consensus research. And then, maybe in a couple of years, it sounds like a long time, but in a couple of years, I'd like to get into more of the math side of things and proving these things so that I can potentially run my own execution environment on Ethereum would be kind of cool. Maybe that won't even be needed. Maybe ETH2 as a state will be enough, and other side chains will be the execution environment. I don't know. But either way, like for example, you can see the proof for this math. So I can't even, personally, I can't even break into this math without looking at the proof because I won't understand why it's all working, what's happening. And so it's not in the scope of this video, and so it's not going to happen. Anyways, proposition 7.1, let x equals, n1 all the way to, x to the 1 all the way to x to the n. So it's a finite list of n values where x is less than or equal to a, greater than or equal to a, less than or equal to b, and let x1 towards xn be sampled without replacement from x. Okay, the following holds, I guess, holds. And is Solomon where I equals 1. Sorry, I'm just going to read it in my head mostly. And this is not math that I can just do off the top of my head. I'm not going to lie to you. But it is math that I can start understanding and working through, and then, when I get a pen and paper eventually and sit down, making sure that I come through these parts again and go through them later on. xi minus n e and x is less than. Okay, suppose the assumptions, okay, so we're assuming that the assumptions are met, and then we're also going to assume that the committee equals 2 to the L. Okay, then the conjunction of the following events, we purposely skip the height of 0. So we only go to the height of 1. I'm guessing this is epoch 1, epoch 2, epoch 3. Let's see. We use the hypergeometric distribution model. That is, we consider the set of x to equal x1 to xn, representing the validators v. Okay, where xj equals 1. So I'm assuming xj equaling 1 would be the epoch 1. If the jth, oh no, not epoch, it's the validator. This is validator 1. We're changing that now. If the jth validator is honest, oh, and 0 otherwise. Okay, so it's where x of j, so a certain x. Okay, so you're just gonna get 0 or 1s. So if it's honest, you'll get a 1. If it's dishonest, you'll get a 0. So I guess you could add up all the numbers at that point, and you would know very easily how many. So if you know you're gonna have, let's say, a certain amount of s or a certain amount of weight, and each weight is 1. And let's say you knew that you had 100 people in your committee. Let's just keep it simple. Then if 0 were dishonest and 1 was honest, that would allow you to add up, let's say, 66 honest validators and know that it was over 2/3. So that's kind of what this is showing, I suppose. They're adding up everything and they're making sure it's greater. Then 2 to the power of 3, but then and this is where you're getting that 1/3 for dishonesty. You're trying to make sure that you're still honest and you're not at that dishonest threshold. Let x1 towards x whatever 2 to the I minus 1 s be 2 to the I minus 1 s, okay, samples from x without replacement. Then for each j, 1 is less than or equal to j. So j is between 1 and that same number. I like how the Teslas do that too, like the sexy kind of thing. That's like sexy. Yes. Anyways, the x to the y equals 2/3 plus this weight. Okay. And there's the full equation there. Oh gosh. So this is where they start, I suppose. And then they simplify it out. 2 to the I minus 1. Then you go 2 to the I minus 1, 2 to the I, s, 2 to the 3 plus, okay. Oh gosh, we continue. Then we compound each either I, the sum of xj's. Oh gosh, I'm not gonna lie. Why are you confusing me with all this math for? I didn't want to read it all anymore. I'm gonna go through it all later because this is too much math for me. It's 10 a.m. Oh shoot, I gotta go soon to try and give out this bike. Anyways, with the last inequality results from the proposition 7-point run, we're calling that n equals to the ls. The probability of each event, e to the I, I guess each event for a certain, is it not slot anymore? It's a validator. Can't remember. They keep changing. I think I is still slot maybe. When considered independently of each other is then bounded below by this value. Using the intersection bound on all, I guess events, either the I, we get the first inequality in the desired statement. The second inequality holds by comparing denominators. Remark: it suffices to also use Hoeffding's inequality with a binomial model where the validators are assigned as honest or Byzantine with replacement. We leave it as an exercise to the reader that this method immediately gets the weaker bound. Okay. Element. This event is less than 1. This element of the exponent. Man, I hate math so much. I love math papers. I just hate math. I like proofs. I like discrete mathematics. I just don't like probability. I don't like algebra. I don't like calculus either. I don't like curves, and I don't mind calculus, but still. While the binomial model is only an approximation, the model with replacement is strictly more mean reverting than the model without. So the approximation is in the correct direction for us. This could be made rigorous with, for example, coupling methods. We use the weaker bound because it is algebraically cleaner and loses very little compared to the stronger bound. It can be seen that the exponential terms in the result of the proposition in 7.2 is fairly small. Exponents from the terms 7.2. Okay. When epsilon is in the order of the root of s. For example, when c, which is equals 64, which I think is what you get, or is it 128? Can't remember. So when c equals 64, a power of 2 actually makes proposition 72 work cleanly. I think this is why you get the numbers you get when I was going through the Theorem 2 economic review. The numbers you get from some of these, 64, 128, why do we use these numbers for committees and slots? Is because it makes a lot of this math work better. So even though I don't like going through the math, I understand that this math is why you need to do things the way they're done in these networks. Though it is certainly not a crucial part of the bound. And thus, s equals 900, picking epsilon equals 30, meaning we have as many as 17,280 Byzantine validators out of 57,600 gives a probability bound of around 85%. Okay, and then changing this variable, which again it goes through the appendix, but not really important, to 40 jumps the probability to 97%. But it just shows how changing the exponents in the equation can lead to variations in the probability, liveliness for this assumption, I would assume. Lemma 7.3, suppose the assumptions are met, then if the view of the total view at a certain time plus this, the committee, then if that justifies a new block, if the network justifies a new block, B, and it's not in the justification view of the network at that time, B must be a descendant of the last justified block. Oh, so we're assuming the assumptions are met. Okay. And so it's saying if in the network view at a certain time a block's been justified, but that is not in the justified view, or not in some J view, I guess it doesn't have to be justified view, then B must be a descendant of the last justified block in this view. which I guess makes sense because if the assumptions are met, then this justified block is in the blockchain. So let's look at the proof. Proof, recall that honest attesters wait for halftime before attesting to their assigned slot. Thus, in the upcoming epoch, J, all of the honest attesters in this epoch attest in the time period T plus half. Okay, so they're going to attest in that time period if you're honest, because you attest, you wait halftime, then you attest. So if you've seen it, you have time to see it, and then attest, and then time plus whatever time it takes you to attest. Because we have half synchrony, it means their views during this period all include, I guess, this network view at a certain time. By the nature of algorithm 4.1, which is above somewhere, this means that all of the block proposals and attestations must be to either a descendant of Bj, or block J, which is the last justified block in the network view at a certain time, or a descendant of some new block which is justified in epoch J, this new epoch. Basically saying either this block is a descendant that was justified or it's a new justified block, but it's a justified block of some kind. Our lemma only fails in the second case, and if some new block in this epoch obtains 2/3 of the attestation of this epoch. Luckily, the chicken and egg favors us. It is possible for Byzantine validators to propose a new block, B prime of J in that same epoch, that's not a descendant of block J. However, it would be impossible for that block to receive enough votes in that same epoch, as all of the attestations before that block are justified must already have gone to that other block. Also, you can't vote twice and all that other stuff. Thus, we know that if we justify a new block, it must be a descendant of block J. And then we have the theorem, which I will go through. I'm just trying to see how far I am. Jeez. Okay, we're almost at 8. I'm going to get through this quickly and then go through. Because it is just a theorem, I'm just going to read through it this time. And then just try and get through this quickly. I'm going to head to the soup kitchen, try and give away the bike, and then head back into more of the econ review. But I'm going to do this quickly. I'm going to leave here at 10:20, 13 minutes. Let's see. Theorem 7.4, justification probabilistic liveliness. Suppose the assumptions in A are met, and suppose we win the equivocation game corresponding to the first slot with probability R. Let block J be the last justified block in the in this view. Then the network view at the certain community slot, I guess, or the justification slot, will justify a new descendant of block J with probability of at least this probability. Proof. We can think of the first slot of this epoch, so at time and time plus 1, as an equivocation game with S validators. HO honest and BO Byzantine. So just H honest, B Byzantine. Where all the options are either this block or a descendant of this block. Thus, with probability R, one of these options received at least 2/3 of the weight to attestations after that certain justification slot, depending on how many validators there are. We call this winning block the block that wins. Ideally, block W is simply just the block, like the justification epoch block. All this is not necessary. For sake of weighting in algorithm 4.1, note that against any other option in the equivocation game, block W's weight is winning by at least 2/3 minus that malicious amount of 1/3. So you got to win by at least 1/3. By an intersection bound with probability at least, again, a little bit different this time, I guess, the probability. I guess you don't have this part here. We also satisfy the events of proposition 7.2. We now show that when these events are satisfied, all remaining honest validators in slot, that justification slot plus 1, and you're going all the way up to the justification slot plus the next justification slot plus 1, will vote for the winning block or a descendant. So if you're honest, you're going to continue voting for the winning blocks or winning block or descendants of winning blocks. Consider the slot just after the justification slot. Okay, because of E1, the first event, we know that the Byzantine for the next one is less than 1/3. So even if all the B1 potential Byzantine actors conspire to vote for some other option, the weight advantage of this winning block cannot be diminished to 0 by the time the honest validators vote at the next epoch. This means that all honest validators will keep attesting to the winning block or a descendant block, which is an honest proposer in this slot. The next slot, in the next slot would propose this next slot as a descendant of the winning block, for example. This is all like repeating itself, but yeah. By E1, we know that the winning block gains at least 2/3 of weight, while a rival block gains at most 1/3, because we know that the Byzantine actors are at most 1/3, or a little bit less than 1/3 during this slot, which means that the weight differential preferring the winning block changes by at least that amount, which is going to equal 1/3. So again, you can always know what the winning block is because the winning block is going to have 1/3 or more weight, because you take the honest nodes minus the dishonest nodes, and you should always get at least 1/3, hopefully above. This means by the end of slot, the new slot after that slot, the winning block is now winning by at least a weight of 2s3. Basically meaning each slot that goes after the first winning block slot or winning slot, the weight just continues on top of that block. Each slot that continues. So then you have 2s3, then you have, 1, and then, whatever. And that's what was being shown over here. Just that at each event, you're going to continue having different heights. And, adding the weight of each block to the winning block so that you continue winning. Oh, it's gonna explain it here too. That's a lot easier. Okay, yeah, now we consider the second event and the next two slots. Okay, between them we know H2 plus H3 is going to be less than 2s/3. So even if all the Byzantine actors conspire, they cannot destroy the winning differential of the winning block, which by the end of these two slots will be winning with at least weight. Again, I'm not going to repeat these things over and over again, but yeah, it's just going to keep going 4s/3. Inductively, this logic continues for all remaining slots in the epoch, specifically all honest validators attest to the winning block or descendant. Here, the structure of algorithm 4.1 is important because while honest attesters may and probably will attest to new blocks, the weight of their attestations are added to that of the winning block as well. We have thus concluded that during all remaining slots, the winning block accumulates all attestations from honest validators. After that, justification slot, it has at least 2s/3 votes with probability R. Then we know it picks up weight at least H1 plus H2 all the way up for a total weight of, again, not going to repeat that big equation out, but that is the weight, and it's 2/3n. total weight needs to be greater than 2/3 of the entire weight that has happened throughout the entire epoch. That's all that matters. This part right here. Okay? This is all just trying to explain this ending part right here. So we indeed achieve enough weight for a supermajority link. So we're proving that this 2/3 n is correct. To prove that this justified block is different from the winning block, we need at least one honest validator to propose a new block on top of this justified block before or in the first epoch of this new, attested epoch of the winning block. Since the justified block receives more than 2/3 of the votes in its block, there are more than 2/3 honest validators in that block. With chance of no honest validator proposing a block on top of, I guess, this block J in the block J is then bounded above by 1/3 to the C minus 1, which is vanishingly small. Okay. So I guess the more validators you have, then in the committee, the larger the committee, the less chance that none of the 128 validators in that committee will not propose on top of a block. If you only need one, then at least you should be good. Probabilistic justification leads to probabilistic finalization. So this is just basically taking the exact same proof we just did for justification and now saying, well, if we take these same rules and we just say if something's been justified and built on top of it for a certain amount of blocks, then it's finalized, then you get the same logic. So the main theorem is the following. Theorem 7.5, finalization probabilistic liveliness. Assume the probability of justifying a block, as in proposition 7.2, is independently probability is greater than half, greater or equal to half for each epoch. The probability of failing to finalize a block in the next n epochs approaches 0 exponentially as a function of n. Proof. So this is, I guess, notes. Recall from the definition of finalization that finalization happens if a chain of consecutive epoch boundary blocks are justified. In particular, if one justified block finalizes an adjacent epoch boundary block, they are finalized, with k equals 1 in the definition of finalization. For this proof, let's call this k equals 1 final. So this is just 1, k equals 1, not the whole k equals 2, k equals 3, stuff we're going to do before, just k equals 1. We consider an epoch a success if a block is justified in the epoch, and a failure otherwise. Thus, if two adjacent epochs are successful, which means two adjacent epochs have been justified, we finalize a block. You finalize that first block. So you have a block here that gets justified, and then that's successful. Then look at that. We get another justified block. Successful. This first justified block then becomes finalized. This one is justified, and then another one becomes justified, and this one become finalized, and that's a blockchain. Therefore, the probability of not getting k equals 1 finalizations in n epochs is the probability that no two adjacent epochs out of the next n are successful. And we've actually had a lot of epochs on Madasha so far that have been justified and not finalized because of the weight of the network in the activity leak. Although we're probably pretty close soon. I think last I checked was at 55% participation, and Madasha needs 66% to be live again. So I'm really excited to see how long this inactivity leak goes for, and I'm really excited to get my validators joining. But we are at epoch 17,787 currently, and we are at slot for Madasha above. You can see we are at slot 567,193. Oops. Wait, no, it is still live. Yeah, and now it says 94, and every 12 seconds, I'm pretty sure, it should keep going to a new slot. And once my validators are active, I should be able to do a lot more showcasing what's going on. Using the independence assumption, this has the probability of this. I'm not going to go through it right now. Because for a particular I is greater or equal to n over 2, there are I plus 1, n minus 1 ways to select I failures. Again, not going to go through a page of math at this point in time, but I will try and understand it from a high level and go through it. Okay, since the probability is greater than half, since p is greater than half, we know that p is greater or equal to 1 minus p. So the sum is bounded above by, okay, and then it's just trying to do math. Not gonna say it right now. I'm just gonna take it as fact. It is well known by example induction. I hate see, this is where I do enjoy proofs and induction and all that stuff, but no. For the nth Fibonacci number, which we know is of the form this, sure. The second term vanishes as n approaches infinity, so our desired quantity is bounded above by, okay, by this. We have the bound, the square root of p bracket 1 minus p is less than or equal to half by the MGM inequality, AMGM inequality, so the failure rate is bounded above by, anyway, which goes to 0 as n approaches infinity. So basically, if you continue having rounds, your failure rate approaches 0. So this is why you have to have infinite rounds for this type of stuff. Finally, recall that we are only looking at k equals 1 finalization, so the chances of k equals 2 finalization can only theoretically increase. Though in practice, they should not happen in good synchrony conditions anyways. Interesting. Sorry. In the cases where we fail to finalize a block in n equals 5 epochs with 3 failing epochs, S denotes success and F denotes failure. Failure with respect to proposition 7.2. Theorem 7.5 is agnostic. So let's look at it first. You have the root, you have success, you have failure, you have success, you have failure, you have success. You're fine. You have the root, you have failure, you have failure, you have success, you have failure, you have success. I guess you're also fine. I don't even know the difference. It doesn't matter too much to me. The point is, as long as you have a success, eventually you should be able to continue going and have another success and justify another block. But you need 2 consecutive successes in order to achieve finalization, apparently. So I would assume here you wouldn't have finalization. Here you wouldn't. Here you wouldn't. Here you wouldn't. Here you wouldn't. Here you. I guess we're showing all of us times when. Ooh, yeah. This is saying that we fail to finalize even with n epoch. So sorry, this is all cases where you fail. That makes sense since we failed in all of these cases. Theorem 7.5 is agnostic to the justification probability P, and now we obtained it. This means if we tweak the protocol, change the assumptions, etc., and obtain different bound estimates for P than we do for the current Theorem 7.4, our result still holds. For this reason, we use P as an input to Theorem 7.5 instead of reusing our actual bound in Theorem 7.4. A secondary effect of abstracting away justification liveliness is that the technique here can be used to prove finalization probabilistic liveliness for general 2-stage protocols, not just GASPER. It could even be extended easily to protocols with 3 or more stages, though the bounding would be different. Regardless of that protocol, or P, as long as it is at least half, as n increases. The probability finalizing a block increases rapidly, getting around 99%, even for P equal to half after n equals 20. So again, the more n equals 20 epochs. The more rounds you have, the chance of finalizing a block, eventually it increases exponentially. So the fact that you have liveliness regardless, and you have 99% probability of finality after 20 rounds, 20 epochs, is pretty awesome. And then you add the inactivity leak to add even more safety. Table 1, the probabilities of not finalizing blocks in n epochs, with P, the probability of justification within each epoch. So you have the probability increasing, the probability of not finalizing any blocks and any blocks. And then you can see how here, with probability of half, and then you can see how with probability of 2 over 3, it is even lower, like it's just even better. Finally, ending off chapter 7. We technically get plausible liveliness for free from probabilistic liveliness, so why do we treat them separately in this paper? For one, plausible liveliness is an immediate consequence from the rules of the protocol GASPER and requires very few assumptions, while probabilistic liveliness, which is, I guess, a stronger assumption, is dependent on, well, I'm not sure if it's, anyways, on probabilistic assumptions such as network synchrony, and is more fragile with slight changes to the protocol. And I say it's more fragile, but it's more robust in terms of you need a system that can work in terms of a lot of different changes to a system, instead of being able to change a bunch of things and be like, okay, well, you didn't work in this one system, therefore it doesn't work anymore. In particular, one of our treatment assumes that all validators have the same stake, which again isn't realistic in Ethereum 2.0. An assumption that can probably be relaxed but would require much more work, which is what Ethereum is. Thus, we choose to present plausible liveliness separately to emphasize that even if these assumptions are not satisfied in real life, plausible liveliness remains. Secondly, the emphasis of plausible liveliness is that honest validators will never be required by the protocol to voluntarily slash themselves to continue. I think that's one of the most important parts of all this, is that if you're honest, you should never have to lose your funds to continue the protocol. And the emphasis of probabilistic liveliness is new blocks will probably be justified or finalized quickly. This allows for increased safety. For example, Madasha, we don't know that blocks will be finalized quickly, which is why we have this long inactivity leak right now. It's been lasting weeks. But that's actually a good thing because you still have liveliness. You still have, the beacon chain running. And eventually, the stake should get to a point where when these validators get activated, we should continue and be active. So what I would see is when Madasha gets active again, I think the mainnet beacon launch isn't far after. But that's all for me. About 47 minutes this time, not too bad. Almost done. I'm going to try and finish the paper tonight, hopefully, and also do some of the ETH2 economic review paper. That's all for me. I hope you all enjoyed the paper. Feel free to read it on your own. It's been very enjoyable so far. And yeah, leave a comment or a note if you enjoy it, or if you read this. I love to, get